the last lesson of chapter 7. Woo-hoo. Which means we'll have a test next week.
Yeah.
Okay, as a warm-up, as a review from Tuesday's lesson, determine whether the dilation from A to B is an enlargement or a reduction. Then find the scale factor of the dilation. What do we think for number 1, reduction or enlargement? Reduction is correct. A is my original. B is my image after the dilation. So to find the scale factor, you got to find a length, and it's easiest to find a vertical or horizontal, so you don't have to use the distance formula. And you want to write the scale factor, which sometimes we use K, as a ratio of the new image after the reduction to the original goes on bottom. And I told you a way you can remember that is if this is a reduction, this number should be less than what? 1. Yep. So 1/2 would be the scale factor. All right, number 2, reduction or enlargement? Enlargement. Here's A, original, to B. I counted this side, you could count the other side. So the scale factor was 2 for that one. Okay. So this last lesson, it's kind of more just like real life applications of proportions and ratios. We talk a lot about like scale models, you know, when you're like given a map and it's like 1 inch corresponds to 40 miles. That's technically like a ratio. And what else do we do? That's pretty much it. We do a little bit of like unit conversion, which my 7th hour told me you guys have done before in 8th grade physics. So it'll be a good flashback to that. All right, vocab for us before we get into some examples. So obviously the title of this lesson is Scale, Models, and Drawings. So basically what that is, it's an object with lengths that are proportional to the object that it represents. So sometimes before cars are made, they make like a small like model of the car, okay? Obviously it's not the same exact size as a real car, but just a smaller model. Or that's an example of like a scale model. We can write these down if you want. Example, cars, they'll make a model. A scale drawing could be like a map, or if you've ever seen like blueprints of somebody's house, obviously it's not the same exact size as a house, but it's just a smaller scaled version to represent the proportional like length of the actual house. So like blueprints I think is a good one as an example of a scale drawing. Okay. These two come up a lot. They might ask you for the scale, or they might ask you for the scale factor, and they're two different things. Okay, so I really want to like differentiate the difference between scale and scale factor. The scale is a ratio of the length of the model to its actual length. Model, that should say or, I think. Model or drawing. To the actual length. The label, the big difference with the scale versus scale factor is the label or the units are a part of the ratio. Okay, so for an example, like a scale on a map might say 1 inch on a map represents 50 miles in the actual distance. Okay, it could be written like that. It could be written as a fraction. You guys know that. We can write ratios in both those ways. More commonly actually written this way. So with this one, your labels don't have to match. They shouldn't match. Because that's what we're like comparing is from the model or drawing to the actual length. So these labels don't have to be the same. And that's a big difference between that and a scale factor. We've actually been talking a lot about scale factors, right? That K variable we just found, that was a scale factor. We talked about similar polygons, similar triangles. We're always like finding the scale factor or the ratio of like the corresponding sides. So a scale factor is a unitless, so there's a big difference. You won't see units written here. No labels or units. It's still a ratio, model length to actual length. So usually it's model to actual. So an example could be like 1 to 32. We don't have units, or you could do 1 to 32. Here's a big difference with the scale factor. If the units don't match, I'm going to have to convert it in order to get like a meaningful relationship between the actual distance and the scaled distance. So what I want you to write down is if labels don't match, and we'll do a couple examples of each. You get to do a little dimensional analysis, which is probably what you've done in physics or in science. Do a conversion. I spelled that wrong. Oh no, that was right. It looks weird. Do a conversion so they match. Okay, and then just like with normal ratios, if we can reduce them, we want to reduce them. All right, we're pretty much just going to do like 3 problems. Each problem has like a couple questions, but let's practice some. Here's an example of a scale. It says the distance between Boston and Chicago on a map is 9 inches. Here's a scale. Notice how it has units. The scale of the map is 1 inch corresponds to 95 miles. What is the actual distance from Boston to Chicago? I know a lot of you could figure this out like in one step, but we're just going to practice like setting up the proportion. So that's what we're doing in chapter 7. All right, so my scale is a ratio of my model to the actual. So we know the model, which is 1 inch, represents 95 miles in the actual distance. So if I know that on the map, Chicago and Boston are 9 inches apart, I want to keep the inches consistent with my proportion. How many miles are they actually apart distance-wise? Now we have this nice proportion. We can cross multiply, but again, I know a lot of us could have just done 9 times 95, which is 855 miles. Okay, follow-up question. Suppose you travel at a speed of 55 miles per hour. That's an mph, means miles per hour. How long would it take you to travel from Boston to Chicago? All right, let's see if you guys remember this from 8th grade physics. Do you guys remember that little formula that relates distance and time and rate? Alex? What does P stand for?
I don't know, I just remember from the physics for
Okay, you think you know? Oh my gosh, you look like
it's dirt.
Dirt. That's what I was like before.
Distance equals rate times time.
Yeah, our distances are rate times our time. We actually use this. We use this formula in calculus. I'm trying to think of which one you're thinking of. What did you say?
I don't know. I was in this like physics room and it just had like a bunch of like.
P normally means pressure.
Maybe that's. I don't know.
Oh.
It was also a Spanish room for some reason. Yeah, it was like Spanish and then there was science.
Wait, what was the formula?
I have no idea.
Oh, okay, well.
I don't know.
Okay.
Come on,
Pressure.
So kind of similar to the last problem. I know a lot of you could have figured it out without like setting a proportion. I'm sure a lot of you could figure this out without setting an equation, but we can do this. All right, we know our distance. What's our distance between Boston and Chicago? And I just kind of want to show you a little bit of like the unit cancellation thing here. We know our rate, the speed at which we're traveling, is 55 miles per 1 hour. I'm going to write it like that to show you the unit cancellation here. And we want to figure out how long. So what's our time? So I'm going to times both sides by reciprocal here to solve for time. I mean, you could also divide by this fraction. But like I said, I want to show you what happens with the units here. I'm going to times both sides by the reciprocal of this. So that essentially undo that. And what ends up happening here is I have miles divided by miles, and I'm just left with hours, so that makes sense. That would give me a unit of measuring time. 855 divided by 55 would be 15 and a half hours. Whoa. I accidentally swiped it with my pinky. Okay. Next one. A miniature replica of a fighter jet is 4 inches long. The actual length of the jet is 12.8 yards. What is the scale of the model? All right, so when we're talking about a scale, that's when the units don't need to match. And they're included in the ratio. Okay, so usually they're written as a ratio of the model to the actual, but technically they don't have to be. You can technically write ratios either way as long as when you go to set up a proportion, you're consistent with it. So we know the model, or the replica, whatever you want to call it, is 4 inches long. And we know the actual jet is 12.8 yards long. So this is technically a fine answer because the units don't match, but we want to reduce, not in the way you're used to. So what we've kind of done before, because we don't like decimals and fractions, is we've done like 4 divided by 12.8 and converted that fraction or that decimal to a fraction, which is fine. I would accept that answer. But typically with scales, usually like the smaller model or drawing is a 1. We want to know like for one of these units equals how many units on the actual. So when you're writing a scale, a better answer, so again, I would accept this reduce, but a better answer would be to divide these both by 4 so that you can figure out what 1 inch corresponds to on the actual jet. And again, it's okay that's in terms of yards. So 12.8 yards divided by 4 is 3.2 yards. So that's probably technically like a better answer. That 1 inch on the replica jet corresponds to 3.2 yards on the actual jet. Okay, there's an example of the scale. So units don't need to match, and we leave them in our answer. Notice how number 2 asks us for a scale factor. Scale factor, that's different. That's my unit list. So no units, only numbers in the ratio, and units need to match. Or labels, whatever you want to call them. Now, unfortunately, what I have right now in my scale is inches and yards. Those are not the same units. So here's a little flashback to your science career. I feel like you do this in chem, too. What year do you take chemistry? Is that like a junior?
Yeah, they're
Sophomores? Sophomores take chem? Do you guys do this in chem, like dimensional analysis, where you like do a bunch of the...
No. Did you guys doing that?
And like cancel out
I don't even
units?
know what we
Yeah,
You guys are doing
like that.
Yeah. Like,
It's like that.
Yeah, because it's like grand.
I just remember doing it when I was, we did it in Chem when I was in high school. It was like converting like miles per hour to like inches per second or something like that. Maybe. Okay. So, sorry, I'm getting excited. So basically, it's a little bit different because we're not converting it to like inches per seconds or something like that. It's not a rate right here. We're just trying to get these units to be the same. So I'm gonna try and relate like inches and yards, and you'll notice what ends up happening is all our units will cancel out. So we'll get a ratio with no units. Okay? So we need a relationship between inches and yards. Now you probably don't know how many inches are in a yard, but you know how many inches are in a foot, and you know how many feet are in a yard, right? How many feet are in a yard? 3. Okay. So since I want my yards to cancel out, I need one in the numerator, one in the denominator. I need them like kitty corner. So I know that for every 1 yard, there's 3 feet. Okay, like I said, you might remember doing this in physics. That's what my 7th hour told me. So these yards cancel. So if I were to go through and do the math, right now I'd have a comparison of inches to feet. But again, I want the units to be the same. So I'm going to need to change the feet in terms of inches. How many inches are in a foot? 12. All right, where would I need to put the 1 foot? Would I put it up here or down here? The top, because I want them to cancel. So for 1 foot, there's 12 inches. So this works out nicely because then those cancel. And so do the inches. So this is how you can get your scale factor. All right, so to multiply these, please, you don't cross multiply fractions. That's proportion. You multiply straight across. We multiply fractions. So you get 1 over 115.2. Or you might see it like on the back of the textbook or like on the worksheet key. You might see it written as a ratio, but I'm okay with either of those answers. I usually write ratios as fractions. So either of those are fine. All right, so let me ask you this question. So that's our scale factor. How many times as long is the actual? No, how many times as long as the actual is the model jet? How many times as long as the actual is the model jet? Any guesses? Now that we know our
115.2.
Exactly. It's just 115.2 times as long. Once you have your scale factor, essentially, you guys, that's what that means. Okay, just like think of the dilations. If our scale factor is 2, that shape was like twice as long, right? Oh, I'll put times. So if they ask you that type of question, you need to know the scale factor. How many more times? Because this gives us a comparison when they're in the same units. Okay, so we can say that. We wouldn't have been able to tell that from just our normal scale. All right, one more problem. Gerard is making a scale model of his classroom on an 11 by 17 inch sheet of paper. If the classroom is 20 feet by 32 feet, choose an appropriate scale for the drawing and determine the drawing's dimension. Okay, so his actual classroom, I'm going to draw that here. Is 20 feet by 32. I don't really know which direction it is, but whatever, it doesn't matter. 20 feet by 32 feet. So I want to model it with a piece of paper. And my paper is 11 by 17 inches. So obviously I'm going to orient the paper hamburger way. Did you guys used to say that in elementary? Hamburger, hot dog?
Yeah.
Hold your paper hamburger. Remember? Okay. Obviously we're going to do it that way if I'm drawing my classroom this way. So let's see, 11 inches by 17 inches. The first thing we want us to do is choose an appropriate scale for our drawing. So that is one that includes units, and the units don't need to match. So what I'm going to do is I'm just going to kind of compare my side lengths here. and see if I can figure out about how many times bigger is the actual classroom when compared to my paper. So just by looking at the numbers themselves, if I start out at 11, it's almost like 2 times bigger. Converting just 11 to 20. Again, don't worry about the units for just a scale. It's almost 2 times bigger. Same with this one, right? It's almost 2 times bigger. Or another way you could kind of set this up is say, all right, what's my comparison for the width of my classroom to the width of my paper? I think that's exactly 1.8 feet for every 1 inch. Okay, that's a scale. Or start with your length. You're like, okay, 32 feet of my actual. That was 1.9 feet for every 1 inch. So we're going to need to round up because we don't want to round out of paper. Okay. So by crunching the actual numbers, that helps you kind of see what exactly we need to scale. And so kind of my little guesstimate of like 2, as long as we round up to 2 feet for every 1 inch, then we will not run out of paper. Okay, does that make sense? So you can calculate what it is or just find one that will work for both. So you'll see when we go to actually find like how much of the paper we're going to use that we won't run out of paper by using this scale. All right, so here's my scale. So again, that one, the units don't need to match and we want to keep the units. You could also write this as 1 inch represents 2 feet if you wanted to do this. That's fine. Just a different way of writing the ratio. Okay. So there's our scale. So let's determine if this is our scale, how much of our paper are we going to use? What would the drawing's dimensions be to represent exactly the 20 by 32 feet? Okay, so you can set a proportion to this. We know that 2 feet is going to represent 1 inch. So in my classroom model, I'll do the 20 feet first. 20 feet, how many inches of my paper is that going to take up? 10. 10. To model it like exactly 10 inches. Okay. If I'm calling that my scale, I'm only going to use 10 inches of my paper. Okay, so you could probably figure out the other one without setting up a proportion, but let's go through the math here. So what about the 32, the length? How many inches is that going to be? 16 inches. All right, so since my paper was 11 by 17, do you see how by rounding up, now we won't run out of any paper, and we can cut our paper exactly if we want to for our drawing to model this. So to answer their question, determine the dimensions of the drawing of our paper. It'd be 10 inches by 16 inches. And that would fit on the paper. Okay. You guys, that's it for chapter 7. That's the last lesson you have to learn for a while.
What is UT?